Welcome to Game Theory Online. I'm Kevin Leighton Brown. I'm one of the 3 instructors for this course. The other 2 are Matt Jackson and Yoav Shoham, both from Stanford University. You'll see them both in subsequent videos. This video is going to give you a high-level sense of what game theory is all about and the kinds of concepts that we're going to think about in the rest of the course. First of all, before I go on, let me tell you a little bit more about what game theory isn't. Game theory doesn't use the word game in the way that most of us are used to in common life, and it certainly doesn't think particularly about computer games. Instead, game theory is a way of thinking about strategic interactions between self-interested people. For this reason, it's very important for economics, and also for computer science, political science, psychology, and a variety of other disciplines. What ties all of these disciplines together is a concern for thinking about how self-interested participants would behave in strategic interactions, and also thinking about how those interactions should be structured, for example, by a government or by the designer of a computer system, in order to lead to good outcomes. I'm going to begin by thinking about one such example from computer science. This is an example that involves networking, but don't be scared off by the computer science content. It isn't representative of what will come in the rest of the course, and in any case, I'm not going to assume that you have any particular knowledge about how computers work in this example. I'm going to begin by thinking about this pop-up, which you might have seen in your browser before. And if you're like most people, you realize that a pop-up in your browser that promises slow connection detected, click next to correct, maybe shouldn't be trusted. It might install a virus or otherwise harm your computer, so you probably wouldn't click on this. But the interesting thing is, if you did, this particular pop-up might actually help you. I'd like to think about how it works, and we can use this example to illustrate something interesting about game theory. Before I do that, I need to tell you a little bit about how the TCP protocol works, which is one of the backbones of the internet. So, as you probably know, if you're over here on the internet and you want to communicate with some other computer, which is over here, what happens is that your communication gets broken up into a bunch of different packets, which conceptually are kind of like envelopes with a message inside them that get delivered across the network to your recipient. And when I say delivered across the internet, I mean you don't actually have a direct connection between your computer and your desired recipient. Instead, there's a whole sequence of different computers along the way who pass the message one to the next to get it from you to your recipient. So you pass the message along the network to some computer you're connected to. It passes it to another computer, and so on down the chain until it reaches your recipient. At that point, your recipient sees that the message is addressed to it, and it sends back an acknowledgement to you telling you that it received the message. And that acknowledgement, likewise, passes through a whole sequence of computers until it gets back to you. So far, so good. Here's the catch. Sometimes a computer in the internet is overwhelmed with messages. Let's say this one right here. And when that happens, it handles this congestion in a pretty surprising way. It takes some of the messages that it receives, and it just throws them away. And it doesn't tell anyone. It just deletes the messages until it gets down to a level that it can handle again. And then with the stuff that it can handle again, it continues behaving as it should, passing messages on appropriately. Well, you might wonder then how it is that you end up with reliable communication over the internet, given that every now and then some computer on the internet throws away your messages. Well, the way that this works is that your computer waits a certain amount of time after sending a message to see if it gets an acknowledgement. And if it doesn't, it assumes that the message was never received and sends it again. Here's the part that's important for our discussion of game theory. Your computer also does something else in this situation. It slows down the speed at which it continues to send messages in the future on the assumption that there's some congestion somewhere in the network, and that this congestion can be reduced by bombarding the network with fewer messages per unit time. And likewise, other computers on the internet are doing the same thing, That's why we don't have the network completely saturated. That's why most of the time we get pretty reasonable throughput on the internet, because everybody is balancing the speed that they send messages out using what's called this back-off mechanism in the TCP protocol. Okay, that's all you need to know about the back-off mechanism. I'd like to think about the strategic problem that you face in deciding whether to install this somewhat suspicious-looking piece of software. That is, I'd like to ask, should you send your packets on your network connection using a correctly implemented version of the TCP protocol, which does have the back-off mechanism inside it? Or should you run this program and instead use a defective implementation which disables the back-off mechanism and just blasts the network all the time without any concern for the congestion that it will cause other people or you? Well, this is a bit of a surprising use of language, but problems like this one are what game theorists call games. A game in general is any interaction between two or more people where the outcomes of the interaction depend on what everybody does, and everybody has different levels of happiness for the different outcomes. So let's think about a two-player version of this interaction, which a game theorist would call a two-player game. You might incidentally worry that the internet has a lot more than two people using it, and so that this two-player restriction is going to be a problem. You'll have to trust me, but this example scales very naturally to larger numbers of players, and everything interesting about it would remain true. So in the two-player case, we have a question of whether each of the players should use a correct implementation, whether one of them will use a correct implementation and the other one a defective implementation, or whether both of them will use defective implementations. In the case, so we need to say what happens in order to analyze this. Let's say that when both players use correct implementations, they both experience a delay of 1 millisecond. Let's say that if one person uses a correct implementation and the other person uses a defective one, then the person with the defective implementation manages to flood the network with packets in a way that causes the other person to back off pretty heavily, causing the person who backed off to experience a much longer delay, and the person with the defective implementation to get their packets through virtually immediately. Lastly, let's say that if both people use defective implementations of TCP, then we're again in a symmetric situation where they both experience the same delay, and they both experience a bigger delay than they would have before because there's now a greater chance that their packets will be lost at every stage in the chain, and so it will take them longer to send a message. Well, I'd like to encourage you to play this game with a friend, or to play it even just in your head, or best of all, to play it on the online system that we've provided where you can interact with other students in the class. What do I mean to play a game? Well, this game might not seem very exciting to play as compared to other things that you would call games like soccer or chess. But in principle, all of these games are the same. There are sets of actions that players can take, and after everybody has chosen what they're going to do in the game, there's some result where everybody feels different levels of happiness. This very simple game has each player choose either to use a correct implementation or to use a defective implementation. And once we know what both players will do, we can look at these rules that I've given here and decide how happy both players would be. Of course, nobody likes delay, so the players are trying to minimize the amount of delay that they experience in the network. So if you wanted to minimize the amount of delay that you experienced, how would you play this game? That's kind of the most natural question to think about when you're thinking about a game theoretic setting. But I'd like to invite you to think about a bunch of other more abstract and philosophical questions, which we'll also address throughout this course. First of all, do you think it's the case that all users should be expected to behave the same in a situation like this? Relatedly, if you're not one of the players of the game, but rather you're someone who cares about how the whole system works from the outside, for example, the designer of the network, what kinds of global patterns of behavior would you expect to see emerge? You'll notice that these numbers that I came up with here are a little bit arbitrary, and they're not very precise. It's reasonable to wonder how much these predictions that we can make about how the game should be played and what behavior would occur depend on those numbers. Is it the case that for slightly different numbers, we would expect to see very different behavior? What effect would there be if players could communicate with each other before they played the game in a non-binding way? What effect would there be if players could repeatedly play the game against each other, either for a finite number of repetitions or infinitely? Finally, how important is it how I model my opponent? Is it different if I think my opponent is rational and does something that is in his or her own best interest? Or would I play this game in the same way regardless of how I believe my opponent is thinking about the game? These are examples of the kinds of questions that this course will help you to think about and will offer you some answers to. And the TCP backoff game is just one example of a real-world situation that we can examine using game theory. Throughout the course, we'll describe many more real-world examples that game theory can be used to think about. Thank you for joining us in this course. We hope you have a great experience, and we look forward to seeing you in coming up videos. Bye-bye.